Okay, should we start slowly?
You're the boss, you just say.
Okay, then let's start. So, welcome to this last lecture before the lunch. Yes, the last lecture before the lunch. So today I want to talk about some very recent stuff about structural sparsity and its application in parameterized algorithm. So most of the stuff that I will be talking about will be on some concepts in graph theory and how do you derive various general usage algorithm, parameterized algorithm for sparse graphs out of them. But first I want to introduce basically the main concepts of this whole theory, and so let me start with the very vague motivation. So the first question is sort of philosophical one. What does it mean that a graph is sparse? Yeah? So let's start with a machine learning definition. So let's give some positive examples and some negative examples of sparse graph class. So for example, if a graph has bounded by a constant maximum degree, it should be rather sparse, right? Yeah. Planar graphs are also sparse, sort of. Yeah? You know the theorem that a planar graph on n vertices has at most 3 n edges. Yes? So this looks like sparsity. However, planar graphs, of course, may have vertices of large degree. Yes? It's just the average degree is small. Yeah? Also, trees looks like sparse graphs, right? Yeah? So if you sort of generalize this concept, maybe graphs of bounded trees should be also sparse. Yeah? Okay, so these are positive examples. What about negative examples? Well, for any sensible notion of sparseness, click shouldn't be sparse. Yes? And the intuition is that a biclick also shouldn't be as sparse. Yeah, a complete bipartite graph. It is super dense. Okay, so let's try to go further. Okay, so let's make a first attempt. What does it mean for a graph to be sparse? Namely, the number of edges of the graph is bounded by some fixed constant c. Yes? The number of edges divided by the number of vertices, the edge density of a graph. Yeah, so let me define edge density of a graph as the ratio between the number of edges and the number of vertices, and let's say that this is bounded by a constant. Note that by handshaking lemma, yes, the number of edges of a graph is half of the sum of the number of the degrees. Yes? So this notion, this density of a graph, is half the average degree. Yes? So bounding the edge density is the same as bounding the average degree of a graph. Yeah? So if you look at this definition and think for a while, you will see a problem. Namely, you can do stupid padding. If I have a following graph, I make a click on n vertices, yes? And then I add to this click, say, n square minus n isolated vertices. So like this. Yeah? So this graph has at most like less than n square over 2 edges, yes? And it has n square vertices. Yes? So the edge density of this graph is actually smaller than half. Yes? But like morally, this graph is not sparse. Yeah? Because it has a very dense substructure which is really large. Yes? Okay. So yes, so although the graph is small, the density is small, we have a large substructure, a large dense substructure. Okay, so let's try to get rid of this example, and let's try to generalize our definition by saying that not only the whole graph must have linear edge density, must have constant edge density, but actually every subgraph of this graph has to have constant density. Yeah, so for every subgraph h of G, the edge density of H must be bounded by some constant C that is predefined. Right? So this at least gets rid of the stupid example of the click, yeah? Because the click then would be a subgraph and it has unbounded edge density. Right? Okay, so this notion is actually sort of equivalent to the notion of degeneracy of a graph that I think you have already seen at the lecture of Sackett on the first day. So let me recall that a graph is called D-degenerate if I can order the vertices linearly so that every vertex has at most d neighbors to the left. It may have arbitrary number of vertices of neighbors to the right, but the number of neighbors to the left must be bounded by d. Yes? So observe that a d-degenerate graph on n vertices has at most dn edges, because if I now count the edges by the right endpoints, yes, then every vertex contributes with at most d edges. Yes? And Also, a degeneeracy is hereditary. A subgraph of a degenerate graph is also degenerate because you just restrict the ordering to the new vertex set. Yes? So this means that the density of subgraphs for a degenerate graph is at most the degeneracy of G. Yes? So this thing is actually bounded from above by the degeneracy of a graph. Yes? On the other hand, if I have a subgraph H and its edge density is at most C, then the average degree is at most 2C, by what we said. So it must have a vertex of degree at most 2C. Yes? And now think of the following procedure. I look at the whole graph. It has a vertex of degree at most 2C. Let me remove him and put it on the right of the ordering. Then I've got a subgraph. Again, it has a vertex of degree at most 2C. Let me remove it and put next on the right end of the ordering. And so on and so on and so on. Every time I remove a vertex of degree at most 2C in the remaining graph. Yes? So at any point I will remove a vertex that has so far to the left the number of vertices at most 2C. So in this way, the degeneracy is bounded from above by twice maximum over subgraphs of this edge density. Sorry, there should be density of H here. Right? So all in all, this notion is sandwiched between degeneracy and half the degeneracy. Yes? Good. However, there is still a problem, sort of a problem with this notion. Look at the following graph. I take a large click on n vertices, and I subdivide every edge. Yes? Now you can see that this graph actually is too degenerate. Why? Because I could put all the subdividing vertices to the right of the ordering, all the principal vertices to the left, and every subdividing vertex will see on at most 2 vertices on the right, on the left, while every principal vertex will see nobody on the left because the principal vertices are independent. Yes? You could also show that the subgraphs of this graph have edge density bounded by 2. Yes? So observe that this graph, on one hand, has bounded edge density of all the subgraphs, and on the other hand, it's a philosophical question whether it's sparse or dense. Right? Meaning some people think it's sparse, some people think it's dense. Yes? And for many years, like in many communities, people were looking at this notion of degeneracy or arboricity, which is equivalent, and designed algorithm based on this. Yes? And then the answer to get this kind of theory would be to say that this graph is actually sparse. So in this theory, we take a different turn, and we would consider this graph as dense. Why? Because sort of the issue is that at depth 1, which will become clearer later on what does it really mean, at depth 1 we see a dense substructure. Yeah? Because if we sort of contracted this subdividing vertices, we would see a clique that is dense. Yes? So now we would like to define a notion of sparsity for graphs that would capture the intuition that this graph should be dense. Yeah? Good. Okay. So so far we work with subgraphs. Yes? And now we want to change the notion of embedding of a graph to capture things that are seen at constant depth. Yes? So let me recall to you the notion of a minor. So a graph H is a minor of a graph G if I can find a minor model of H in G in the following sense. Every vertex needs to be mapped to a connected subgraph of G. Yes? These subgraphs are called branches and they should be disjoint. Yes? And moreover, whenever I have an edge between 2 vertices of this graph, yes, there should be an edge between the corresponding branches. Yes? So essentially, every vertex can be smeared on a connected subgraph in G so that the stains that I get from vertices are disjoint and the connectivity is preserved. Now I will say that this is a depth D minor model of H, if basically the same definition, but these branch sets should be local, in a sense that they should have radius at most D. Yes? So this is a more restricted notion. I am able only to have like local stains for every vertex. Yes? So this is our notion of sort of local embeddings. Yes? And observe that depth 0 minors are exactly the same as subgraphs. Yes? Because a graph of radius 0 is just a single vertex.
So just to make sure I understand this,
yeah.
here's a thing, and then you tell me whether I just invented basically this. In round 1, I pick disjoint edges and contract them.
Mm-hmm. I think disjoint stars.
The number of rounds I need for this process, so I think it's central that the edges are disjoint.
I think you need to contract the stars instead of single edges. Because observe that these branches can be arbitrarily large.
Oh, good. Okay,
Yes?
so in round I get to point to a star, contract it.
Yeah. Disjoint stars, contracted. Disjoint stars, contracted. Yes? And in this matter, after
The number of rounds is
the number of rounds, basically this is the same. Good. Okay, so the idea is now in this theory to replace the notion of subgraphs in the definition of sparsity with shallow minors. Yes, so minors of constant depth. Yes? So now we go to the formal definition of sparsity. And the first thing that I would like to really underline here is that in this theory, like sparsity is not a notion of one particular graph. Yes? Because say K10, is it sparse or not? Yes? From one point of view, it's sparse because it is small, or it is not sparse. Sparsity is a property of a graph class. Yes? So a set of graphs, an infinite set of graphs. Good. So for a graph class C, I will denote C triangle, sorry, nabla D, yes, or reduct D, I think it's called, the set of all depth D minors of graphs from C. Yes. So they in particular contain all the original graphs. Yes. The reduct at depth 0 is just the closure under subgraphs, right? Yes. But the larger and larger radius I allow, the more and more complicated graphs I can get. Yes, as minors. Right? And now I will say that a graph class has bounded expansion if whenever I fixed depth D I'm interested in, and I look at depth D minors of graphs from my class, the edge density in those D minor, or these shallow minors, is bounded by a constant. This constant depends on D. Yes? So among subgraphs, I have bounded edge density. Among one shallow minors, I have also bounded edge density by a possibly larger constant. Yes? For depth 2 minors, the same, and so on and so on. And this for every constant D, these constants are governed by this function f. Yes? That associate the bound to the depth I'm interested in. Yes? So this is one notion of sparsity that you can get based on basically this idea of the degeneracy that we discussed so far. You can get also more relaxed notion that is called nowhere dense. Yes? So a graph class is nowhere dense if simply for every constant depth that I'm interested in, I exclude some clique. Yes? So maybe at depth 0, I exclude clique K10. Yes? I do not have K10 subgraphs. At the depth 1, I exclude K20 subgraphs. At depth 2, I exclude K100 subgraphs. And so on and so on. So for every constant D, yes, I exclude some KT of D as a D shallow minor. Yes? So obviously, every class that is nowhere dense also has bounded expansion. Yes? Because basically, every class that has bounded expansion is also nowhere dense. Yes? Because basically, if I bound the edge density in my subgraphs, yes, then in particular I need to exclude some clique, yeah, because the cliques has larger and larger edge density. Yes? Because they have quadratic number of edges. Yes? Okay. However, the converse is not necessarily true. There are classes that are nowhere dense but do not have bounded expansion, but these are sort of degenerate cases. It's not trivial to see it. However, it is also true that nowhere dense classes are actually sparse. In the following sense, whenever I take a D shallow minor of a graph, a D shallow minor of a graph from my class, then the number of edges is not necessarily linear as it would be implied by bounded expansion. It is almost linear. It is like n to 1 plus epsilon for any epsilon that I wish for. Yes? Here this depends on epsilon and D. Yes? We will not concern too much with with this kind of reasonings. But basically, the bottom line is that these graphs are also sort of sparse. Good. Okay, so why we care about these two definitions? Yes? It turns out that they are actually very robust notions that sit on top of this whole hierarchy of sparse graph classes that were studied for many years. So in the bottom of this hierarchy, you've got like simple sparse classes that we already talked about, like planar graphs or graphs embeddable in surfaces of bounded genus, or bounded degree graphs, and so on, bounded tree of graphs, forests, yes? Then you've got classes excluding a minor, or classes excluding a topological minor, for which we have sort of global decomposition theorems of Robertson Seymour or of Groh and Marx. Yes? And then on top of them, actually we have classes of bounded expansion. So bounded expansion already encapsulates all the sort of familiar sparse graph classes, like planar graphs, bounded genus graphs, H minor free graphs, bounded degree graphs as well. Yes? So whenever you get an algorithm for bounded expansion classes, it actually encapsulates all these notions here. And lower dense classes sit even above of this. Yes? So in some sense, this encapsulates all the notions of sparsity that we have studied, apart from degeneracy. Yes?
Why is locally excluding a minor different from lower dense? So what is locally excluding a minor?
For every vertex and for every radius, in a ball of radius this, you exclude a minor, some minor. And this minor that you exclude can be different for different radius. It is different, it is different. Yeah, so on this picture you see also some graph classes I was not talking about, but I will not talk about them at all, yeah? So during this talk I will talk about bounded expansion and lower dense mostly. Yes? Ah, it's actually not my figure, it's due to Felix Riedel. Yeah. Good. Okay. So this theory of sparsity is kind of a new branch of basically in graph theory with algorithm applications, and mostly it was developed by Jaroslav Nešečil and Patricia Sona de Mendes from say 2005 till today. So it's like 10, 12 years old. Yes? So there is a book about it by these two authors called Sparsity. It was published in 2012, and since then there were many, many developments. Also, just for the record, if you want to learn this theory, and your idea is to grab this book and try to read it, this is not a good idea. You'd rather just talk to somebody who knows this kind of stuff, or look at some lecture notes, or some surveys. Good. However, many concepts that were sort of encapsulated by this theory of sparsity were actually flying around in the literature before. The earliest definition of lower denseness that I know of is from '76. It was given by Podewski and Ziegler. It was actually a model theory paper that was about infinite graphs. And they defined it in the infinite setting. And this is actually a brilliant paper in a sense. There is a lot of results there. So basically, in summary, what I will try to convey in this talk is that these concepts of bounded expansion and lower denseness are really robust and fundamental notions that explain a lot about what does it mean sparse. And they have multiple, this is witnessed by the fact that they have multiple very different combinatorial characterizations, and each of those characterizations gives you sort of a different technique or a different tool that can be used algorithmically as well. Yes? And it has many applications both in algorithm, well, in combinatorics, of course, and it has quite a deep connections to logic in computer science. I will not talk much about connections to logic during this talk, but you can also see it in many recently published papers. And the idea is that this lower denseness, or bounded expansion, really delimits the tractability area for many basic problems. And I will show it later on some dichotomy theorems that we got for problems in parameterized complexity. And if you work on sparse graph classes, and in particular on planar graphs or H minor free graphs, you have probably came across the H minor free decomposition theorem of Robertson Seymour, which is technically, well, quite difficult to grasp. And if you work in this with the notions of bounded expansion and lower denseness, you suddenly have sort of less tools because you work with a more general graph class, but the whole setting becomes much clearer, in a sense, and cleaner. So I really appreciated working in this setting because you sort of see the right arguments in the play. Okay, so let me talk a little bit about different characterizations. So in the middle we have the definition of boundary expansion over denseness via those shallow minors. Yes, so I want to go through basically the intuitions behind different notions. I will not define them formally. So first of all, you could imagine a different definition of embedding via topological minors. Namely, now instead of saying that vertices have to be smeared onto connected subgraphs, they need to be mapped to single vertices. But now the edges, instead of staying just edges, yes, they must be mapped to short paths. Sorry, to paths in topological minors. So it's natural to have bounded depth topological minors by just restricting the length of the paths in topological minors. Yes? So topological minors and minors in the normal world, they behave quite differently. Yes? However, in this whole theory, you could define the same notions of boundary expansion and lower denseness using topological minors. And it turns out that not only you get a similar theory, you actually get the same theory. Meaning defining boundary expansion and lower denseness via topological minors gives the same notion of classes of graphs. Good. Then you've got the degeneracy idea. Yeah? So we have had this idea about degeneracy being sort of looking at sparsity of subgraphs, which are depth 0 minors. Yes? And there was this equivalent definition of degeneracy via this vertex ordering. Yes? So the natural idea would be to generalize the notion of degeneracy by looking at larger depth, which means in here, looking at longer paths, sort of, instead of just single edges going down. So this is achieved by those so-called generalized coloring numbers, and this is like a crucial technical tool for algorithmic treatment of sparse graph classes. Okay, next. There is a notion called uniform quasi-wideness. I will go into the details later, because in the second half of the talk I will be speaking mostly about this. The intuition here is that a sparse graph is sort of flat. So if you have a really huge sparse graph, you should see many vertices that are far apart from each other. Yes? And this is formalized via uniform quasi-wideness. The next definition is via neighborhood complexity, in a sense that you've got a graph from a sparse graph class and a subset of vertices. And you are interested in the following question. I now classify vertices according to what they see in A, to the neighborhood in A. Yes? How many classes do I see? Yes? In principle, 2 to the size of A. Yes? Every neighborhood can be realized by some vertex. It turns out that sparsity can be equivalently defined by saying that this number of different types of neighborhood in A is actually almost linear in the size of A and not exponential. Yes? So all these things, yes, all these like combinatorial viewpoints can be used to define the notion of sparsity in the sense of boundary expansion or lower denseness, and there are multiple more in the play. I will not go through all of them. I see a question here.
So when you say neighborhood complexity and you say equivalently defined, for equivalently, is neighborhood enough, or do you need to go to our neighborhood?
You need to go to our neighborhood. I'm glossing over the details here. I just wanted to show you this slide, yes, to show you that these characterizations are very different, yes, in a sense that it really looks like we have a robust notion, yes, that defines some important meta-class of classes of graphs, yes, which admits different combinatorial angles of working with it. Yes.
Every definition is where can we find each definition? We need one paper for each definition. There is one paper for each definition, or there are
sort of. There are many different papers which introduce different concepts and show their equivalence to lower denseness or boundary expansion. Yes, they are not trivial. They are not trivial. Yes. So we have, for example, low 3-depth colorings or fraternal augmentations. There are structural measures very close to generalized coloric numbers and are really useful in algorithmic treatment. You have a game theoretic definition of nowhere density via the so-called splitter game. You have, for example, neighborhood covers, which is really useful for designing distributed algorithms on sparse graphs. Yes? So each of these techniques, each of these tools, gives you a different algorithmic technique in a sense. Good. So this notion of bounded expansion and nowhere denseness, of sparsity, can be applied under various algorithmic paradigms. So here at the school we are most interested, of course, in parameterized algorithm, especially in kernelization. And we have already seen in the literature, many results on sparse graph classes using this toolbox, yielding fast fixed parameter tractable algorithm or efficient kernelization algorithm for different problems on sparse graphs. Yes? There is also a lot of work on approximation algorithm using this regime, meaning it can be used. Yes? And also in distributed algorithm. Yes? And if you look at the logical side, there is also this whole line of work that I will mention later about model checking first order logic on sparse graphs. And it turned out that nowhere denseness and bounded expansion are really well tailored for this kind of treatment. Yes? So we see so far a little bit more areas where applications could be found, meaning this is work in progress. So we think that there should be something to do in sparsity regime, in circuit complexity, and in dynamic problems. But I will not go into this further. And the intuition here is that because we are talking about sort of local embeddings of minors, yes, like we are dealing with local things, this toolbox inherently applies to sort of local problems. Yes, and I will try to make it more clear in a moment. So what are local problems from the point of view of, say, parameterized complexity? We'll be mostly talking about two local problems, and if you look at the literature, actually most of the algorithmic literature either deals with this problem or with this problem or with both of them. So the R-scattered set problem is the following. I've got a graph and integer k, and I want to find k vertices that are far apart from each other. How far? I want the balls of radius r around them to be pairwise disjoint. Yes? This is equivalent to saying that they are at distance at least more than 2r from each other. Yes? So this is the same as, say, 2r independent set, and a generalization of independent set in general. Yes? The sort of dual problem is the r-dominating set problem, where I've got a graph G and integer k, and I want to find k vertices in my graph that r-dominate the whole graph. So every vertex of the graph has to be at distance at most r from one of the picked vertices. Yes? So this is like covering the graph with at most k balls of radius r. Yes? Good. So these are the two local, archetypical local problems from the point of view of parameterized complexity. So what is the archetypical problem from the point of view of logic for locality? So this is model checking for first order logic. So those of you who do not know first order logic, let me introduce it. This is actually very simple. So basically this kind of logic where you can quantify vertices, yes, existentially or existentially, and then you can do some Boolean connectives and you can check adjacency of vertices. So instead of doing the formal semantics, let me again give a machine learning a definition. So first example, I can write the following sentence in first order logic on graphs. There exist vertices u1, there exists a vertex u2, there exists vertex uk, such that these vertices are pairwise non-adjacent. Yes? What is this problem? Independent set. Yes, so I just phrased that there exists an independent set of size k. Now if I write there exists u1, there exists u2, there exists uk, such that for every vertex v is either equal to one of those or adjacent to one of those. What is this problem? Dominating set. Can you now phrase r-dominating set in the same way? Yes? I need to say that v is not adjacent to one of them, but is at distance at most r. Yes? So I could say that there exists the first vertex of the path, there exists the second vertex of the path, and so on, up to r vertex of the path, so that there is so that there are adjacencies along the path. Yes? And the more general problem would be first-order model checking. You've got a formula of this form, a sentence of this form, and you want to check whether the input graph satisfies this formula, this sentence. So this FO model checking in particular generalizes these problems of R-independent or R-scattered set and R-dominating set. Yes? So in general graphs, you can easily see that there's an XP algorithm for this, parameterized by the length of the sentence, because you just brute force. Yes? Whenever you say there exists a vertex, you branch into all vertices. Whenever you say that for all vertices, you branch over all vertices. Yes? However, this problem is like super hard from the point of view of parameterized complexity. Yes? It is AW star complete, whatever it means. Yes? However, there was a long line of work on this problem in sparse graphs, like first unbounded degree graphs, planar graphs, and minor free graphs, and for all these classes, there were FPT algorithms parameterized by the length of the formula. Yes, so some function of the length of the formula times a fixed polynomial. Yes, and the crux here is that first-order logic is provably local on graphs. Yes, in a sense that if you have a formula that has quantifier rank q, which means that it uses at most q quantifiers, it cannot measure two long distances. With a formula with quantifier rank q, yes, you cannot say that two vertices are at distance, say, 2 to the power q plus 1 from each other. Meaning all distances larger than 2 to the power q are actually sort of the same from the point of view of formulas of bounded size. Yes? So this logic can only express sort of local properties, yes, which is sort of also captured by the fact that this independent set and dominating set are captured by this logic. Yes, and the same story was for dominating set and independent set. Again, on sparse graph classes, there was a long line of research on planar graphs, H minor free graphs, and so on, of getting more and more involved parameterized algorithms for them. Okay, so once we have looked at this via the lens of the sparsity theory, lower dense class and bound expansion class, it turned out that we can find really nice dichotomies for these problems. So the first dichotomy, which is probably the pinnacle of algorithmic work in this theory, says the following. Suppose I've got a graph class, yes? Any graph class, provided it is closed undertaking subgraphs. Yes? Then, either this graph class is nowhere dense, yes? It excludes a click at every fixed radius, at every fixed depth, or it is somewhere dense, which means just negation of nowhere dense. If it is nowhere dense, then FO model checking is FPT with almost linear running time. Yes? However, if it is somewhere dense, then the problem is as hard as on general graphs. Yes? So this means that this nowhere denseness, this notion of nowhere denseness, really delimits the tractability, the fixed parameter tractability of the first order model checking. Yes? If you look at more specific problems, say our dominating set, again we have a similar behavior. If you are nowhere dense, then our dominating set has a kernel with almost linear number of vertices. Yes? Again, this k to 1 plus epsilon for any epsilon that you wish for, and this happens for every radius r. Yes? However, if you are somewhere dense, then for some fixed radius r, you are already as hard as on general graphs. So again, these two theorems shows that for local problems, nowhere denseness is exactly the border of tractability. Yes? And this sort of supports this intuition. Good. So during the rest of the talk, I would like to give you one particular proof or nice algorithm that you can get in this field. And for this, I would like I need to introduce you to a little bit, take a closer look on one of those equivalent definitions, namely uniform quasi-wideness. So the intuition is that if you have a sparse graph that is super large, you should find many vertices in the super large graph that are pairwise far from each other. So is this intuition exactly true? Not really, because a star. for any reasonable notion of sparseness, a star should be sparse. Yes? But sort of every two vertices in a star are close to each other. Yes? However, the idea is that if you remove the center of the star, suddenly vertices would be far apart from each other. Yes? So it will be like I will be able to find many vertices that are far from each other, apart from the fact that I will remove some bounded number of vertices. So this definition will be sort of convoluted, but let me go through it slowly. So the idea is that whenever I've got a large graph and a large subset of its vertices, I will be able to find many vertices inside that are far apart from each other, apart from the fact that I will need to delete some small number of hubs. Yes? So a class C is uniformly quasi-wide if the following holds. Let me fix first the radius r I'm interested in. This will mean far. Yes? Then there exists some constant sr. Yes? This will be the number of vertices I will delete. And the function nr. Yes? This will be a function governing how large I need to take a graph in order to find many vertices. Yes? Such that the following holds. Whenever I take a super large graph from my class, and I find a large subset of I take a large subset of vertices. How large? At least nr of m, where m is the size I'm aiming at. Then I will be able to find some small subset of vertices s, of size at most sr. Yes? Such that in the remainder of A, I will be able to find at least m vertices that are r-scattered. Yes? So note here that this function nr governs if I ask for an independent set for an r-scattered set of size m, it will tell me how large this subset A I need to begin with. Yes? And note that the number of vertices I delete, yes, it depends only on the radius. It doesn't depend on m, the size that I wish for. Yes? Okay, so this is a slightly convoluted notion, that sort of tries to capture this flatness of classes. Yes? And the magic is that actually this is the same as nowhere denseness. A graph class is uniformly quasi-wide in this sense, if and only if it is nowhere dense. Yes? So this looks a bit magical. So let me just remark that for fixed class and fixed radius, this bound is actually polynomial. The first proof was like super exponential with Ramsey on Ramsey on Ramsey. Yes? But now we have better proofs that are polynomial. And this proof is also algorithmic. You can find such S and B in polynomial time. And this is like a basic tool for sort of digging structure in sparse graphs. You have a large subset of vertices that you want to understand. You apply this, and suddenly you see many vertices far apart from each other. Yes? And during the rest of the talk, I want to give you a very simple algorithm for the r-dominating set problem, working on any nowhere dense class. And this will be based on some unpublished work with Sebastian Siebert and Szymon Tojenczyk. Good. So before I go to the algorithm, let me give you the following question. So suppose I've got a large graph, and I've got a small subset of vertices A. And I'm only interested in r-dominating this vertices from A. Yes? In what running time I can do it. So let me do a really naive approach. So vertices outside of, well, vertices of the graph, they have some r neighborhoods in A, meaning the vertices that they r-dominate in A. Yes? Two vertices that have exactly the same r neighborhood in A are actually like functionally equivalent, yeah? Meaning they cover the same thing. Yes? So then I partition vertices into those classes. There are at most 2 to the size of A classes. Yes? And I just guess k classes from which I will take vertices. Yes? I iterate through all k tuples of classes. What is the running time? The number of classes is 2 to the power A. Yes? And I iterate through all k tuples. So you've got to the power k times A. Times, you can do it in linear time. Right? However, now sparsity magic comes into play. Actually, this number of classes by this neighborhood complexity characterization will not be exponential in A, but it will be almost linear. So actually, this running time is like A to power order of k. Yeah? Good. If you are familiar with dynamic programming on subsets, I will not go into the details because we will use this algorithm. You can make a simple dynamic programming on subsets for this with running time 2 to the power a, but it will turn out that actually this running time will be better for us. Good. So let me now give the simple algorithm for our dominating set. It will look stupid. Let me take any k-tuple of vertices. Yeah? Let me check if it's an R-dominating set. If I'm so lucky that I already start with an R-dominating set, then I just terminate the algorithm, right? Otherwise, I find one vertex u1 that is not R-dominated, right? Okay, so now I proceed to the second round. Let me be a little bit smarter and at least dominate this vertex u1. Yes? So I find any k-tuple of vertices d2 that R dominates u1. Yes? If it's a dominating set, yes, I'm already happy. Otherwise, I find a vertex that is not R-dominated by D2. Yes? Okay. So now let me be a little bit smarter and find D3 that at least dominates those two vertices that I have already found. Yes? And so on and so on. So every time I'm finding a dominating set that dominates all the vertices UI that I have found. So let me give you the precisely formally the next round. In round I try to find a k-tuple of vertices that R-dominates those vertices that I have found. Yes? It may happen that there is none, yes? But then I am certain that there is no R-dominating set of the whole graph. And I can answer no. Yeah? Because already those vertices I am unable to dominate. Yes? Otherwise, I find it, yes? And if it happens to be an R-dominating set, I'm super happy, yes? And I terminate algorithm again. Otherwise, I find the vertex u6, yes, that is not R-dominated by this, and I just continue. Yeah? So this is the whole algorithm. Okay, so let's analyze it. So suppose I have fixed R, and I have fixed a lower dense class from which I have taken the input to this algorithm. Yes, so each round may either terminate the algorithm, saying yes or no, or we'll just proceed. Yes? So let's look at round I. If I implement now round I, yes, I am interested in dominating a set of size I. So the running time will be like I to power order of k times linear. Right? Good. However, like a priori, this looks really stupid, yeah? Because maybe this algorithm just proceeds with more and more complicated rounds, and I do not have any bound on the running time. Yeah? So now this is where the sparsity magic happens. I will prove to you that this algorithm will always terminate in a number of rounds that is bounded not only by a function of k, but actually by a polynomial of k. Yes? Which means that for every lower dense class C and radius R, the R-dominating set problem I can solve in this running time. Because I have then every round will be like polynomial, so I will apply this algorithm only on I being a polynomial. Yes? So I will get this kind of running time, which is already quite a good running time for an FPT algorithm. Yes? Well, almost, yeah. In bounded degree, we've got to the power order of k. Good. Yes. Observe one thing. With many like planar graph algorithm or bounded genus algorithm, yes, they really need to work with planar embedding. This algorithm is completely oblivious of the graph class on which it is applied. It can be applied on any graph in hope that the number of iterations will be small. Yes? Okay, so I now need to prove this magical fact that the number of iterations will be bounded. Yes? So let's now first focus on case k equal to 1. Yes? So I'm just trying to find a vertex that R dominates the whole graph. Yes? Okay, so I will use uniform quasi-wideness. Let me fix those constant and function from the definition of uniform quasi-wideness. And suppose that my algorithm proceeded for very many rounds, yes, creating this structure that I will call a quasi-ladder of length L. Yes? So we have many pairs di ui, which are consecutive, which are vertices found in consecutive rounds. So for every pair di doesn't dominate ui, but every di dominates all the previous uj's. Right? Good. So let me look. So I have now made many iterations. So let me, and this number of iterations, suppose. So let me look at those UIs and let me apply uniform quasi-wideness to it. Yes? What uniform quasi-wideness tells us? I can find small number of vertices, as r of them, such that within those UIs, I will find then many vertices, at least this number, yes, that are pairwise at distance at more than 2r. Right? Good. Okay, so now let me do some classification on those vertices. For every vertex, let me measure the distance to every guy from my set that I removed. Yes? So say that to this guy I am at distance 10, to this at distance 6, and to this I am at distance more than r, which I will just denote by infinity. Yes? So I do not care about distances larger than r. Yes? So I define this r distance profile, yeah, which is just the distance function to vertices from S capped at threshold r. Yes? So how many distance profiles do I have? Well, this many at most, yeah, because S is small, yes, and this distance profile can take values 0, 1, 2, 3 up to r, so r plus 1, or infinity. Yes? So since my set B, yes, of those distant guys was sufficiently large, I will find 3 guys that have exactly the same profile. That's the pigeonhole principle. Good. Okay, so let me look at those guys. But now recall that actually this guy was r-dominating both these two. He was r-dominating all the previous guys. So let me draw this path. They are of length at most r. So now if I concatenate those two paths, I see a path of length 2r, yes, between ui and ub. Yes? However, they should have been at distance more than 2r, yes, but in the graph with the set S removed. Yes? So these two paths need to cross at some point the set S of removed guys. Yes? Okay, however, this UB, say at this path, the second case will be symmetric. Yes? Now observe that this profile from UB and UC on this vertex was actually the same. So these distances from UB to this guy and from UC to this guy were actually the same. And now I get a contradiction because I see a path of length at most r from DC to UC. But DC was supposed not to r-dominate UC. Right? Yeah, so we got a contradiction. Yes? Hooray, this ladder cannot be so long. Yeah, for k equal to 1. For k larger than 1, it will be actually simpler. So we have shown that for k equal to 1, the number of runs is at most some constant L. Yes? And I claim that for larger, it will be at most k to L plus 1, where L is actually this bound for k equal to 1. How do I do it? Suppose that my algorithm did so many rounds. Yes? P equal to k to L plus 1 rounds. Let me look at the last iteration. Here, I have k vertices that dominates all the previous UIs. Yes? So one of them, yeah, each of this domination needs to be served by one of those k vertices. Yes? So one of them serves at least 1 over k fraction of the previous guys. Yes? So what I do, yes, so this 1 over k fraction is like k to L. Yes? So what I do, I just remove it, yes, and I proceed. Now I take the next one, yes, then one of these k guys serves at least 1 over k fraction of the previous ones, and I remove it, and so on. And if I proceed for L plus 1 iterations, I will create this quasi-ladder for k equal to 1, yes, of length L plus 1. Contradiction. Let me just state for the record that our first argument for this was based on Ramsey's argument, and we had like here a big blow-up. But around a week ago, we presented this during tutorials at our course on sparsity in Warsaw, and this was actually pointed to us by students. So, yeah, we felt the dump after this. Good. So this concludes the proof, right? We have shown that this ladder, this quasi-ladder at the beginning, cannot be longer than polynomial in k. Yeah? Okay, so let me now tell you at the very end how we actually got to this state, meaning to this algorithm. So let me tell a little bit about stability. So suppose I've got an FO formula, yeah, with some free variables. For example, I could say that two vertices x and y are at distance at most r from each other. Yes? Yeah, so this is not a sentence. Yeah? These variables x and y are like put into the formula and they are not quantified. Yeah? So suppose that this is this is delta for two single variables, but this may be like tuples of variables. So this might say state some relation between say pairs of vertices. Okay, so a delta ladder, yes, of length L is almost like the quasi-ladder that I've shown you. Yes? So here I've got a sequence of tuples that are valuations of x. Here I've got a sequence of tuples that are valuations of y. And I should have a positive relation, like here should be delta. I should have delta whenever from every ui that is larger than vj, and negative relation in the other way around. Yes? So this is a stronger structure than we had before. Because before we had a positive relation here, but we had a negative relation only in the matching. Yes? We did not have these things. Yes? So then I say that a graph class is stable if for every FO formula, delta, I've got a finite constant bound on the length of ladder that I can get in this manner. Yes? This definition of stability. And the intuition is that you cannot define long linear orders in this way. Yes? And the actual usage of this definition is that you try to make an iterative procedure, as we did for the dominating set problem, and you want to bound the length of the procedure by the length of the ladder, by the upper bound on the length of the ladder that you a priori know that there exists. Yes? So this algorithm that I showed you was actually our failed attempt at trying to give an FPT algorithm for our dominating set on any stable graph class. Yes? And the nice theorem is that if you assume that a graph class is closed under taking subgraphs, then actually stability and knower denseness are the same concepts. This is a theorem by Adler and Adler based on ideas of Podewski and Sigla from the 76 paper. Good, so to conclude. So this theory of structural sparsity in a nutshell is that basically in the basic definition we try to sort of capture sparsity that is sort of persists under local contractions. Yes? But however, there is an abundance of equivalent definitions that can be used, yes? And there are many applications of this in combinatorics, in algorithm, and in logic. Yes? And the intuition is that it delimits the tractability area of local problems. Yes? So this toolbox is not only applicable for parameterized complexity, but for many other, it is very interdisciplinary in some sense area of study. Yes? And it provides really clean and nice proofs that are compared at least to Robertson's similar decomposition. The caveat of this is that actually when you go through the proofs and you unpack all the black boxes, the constants that you get are really, really bad. Good. So we are running in Warsaw this semester a course on sparsity theory. So if you are interested, we are making really like nice lecture notes from this course, so you can go to this website and see. So far we covered the core part of the theory, meaning the main combinatorial toolbox and algorithmic toolbox of the theory in 10 lectures. So you have there like 60 pages of lecture notes about sparsity, if you want. And our idea is that probably at some point we will turn them into a book. Yes, but this is still in plan. So far we want to focus on writing down nicely the toolbox for the algorithmic design for sparse classes. And thank you for the attention.